Good morning, students. I am YP Verma, faculty at UIT Punjab University, Chandigarh. The topic of discussion today is synchronous machines. We know that machines have huge applications in our day-to-day life. The common example, starting from a small fan to the many application in industry, machine are inevitable for the industrial growth as well as for general purpose work. The machines can be classified on various parameters. One of the simplest way we can classify machines are on the basis of the supply they are using. They can be AC machines or DC machines. The AC machines are of two types, induction and synchronous type. Today the discussion will be limited to the synchronous machines only. The machines they are designed on the basis of certain applications. For what kind of application, which type of machine we need to use. So we can design machines. That is why this classification of the shunt, series, compound type of motors and DCs are they have been used. Another way of the classification, the simplest way of classification is machine can either be generator or it can be a motor. A generator, as we know, that it converts mechanical power to an electrical power. So we supply this mechanical power through these steam turbines, then hydraulic turbines, and in return we get electrical output, and it can be again AC as well as DC. So we call it as AC generator or DC generator. Similarly, the motor, it converts electrical power into mechanical power. Like fan is a simple example of a motor. So we simply switch on the power and we get mechanical motion in return. If we talk about technical definition of this, so in motor we can say that it is a current carrying coil placed in a magnetic field. It induces a force and whose direction can be given by the Fleming's left hand rule. And for generator, we can give the direction of the EMF using Fleming's right hand rule. Now, as far as the construction is concerned, because it is very important to understand the construction of the machine. Here we again very limited to the synchronous generator. Every rotating machine, it has two parts. One is stator and second is rotor. Stator, the stationary part of the machine, and rotor is the rotating part of the machine. Generally, stator carries the armature winding and stator it carries the field winding. But in case of synchronous generator, it is other way round, because the synchronous generator, they are generally used for generation of power supply, like whatever we use in hydropower station, in thermal power station, there we generate power of a higher voltage level. So as a result of that, if we have to use higher amount of winding, so that can ultimately result into a large size of the rotor. And if we use armature winding on the rotor, that can result into certain oscillations of the machine. So in order to avoid that, we place field winding on the rotor and armature winding that is placed on the stator in case of synchronous generator. In synchronous generator, the rotor winding is energized by a DC source to develop the rotor magnetic field, because in generator the simple principle is we need to change the flux, and that flux can be changed either by rotating a coil in a magnetic field or keeping a magnetic field field coil stationary and rotating the field. So that is what we call as static induced EMF or dynamic induced EMF. If you see the construction of the rotor, the stator, it has three major parts. One is the frame, then core and the winding. Frame is the outer part of the machine, as can be seen. You can see this part, the outer part of the machine, and the core, the internal part of the machine. This is generally made of the silicon material, which is permeable in nature, and the windings. If you see here, the windings, we create slots in the inner periphery, and the windings, they are accommodated in this inner periphery, and generally the three phase windings, they are placed in these slots. The windings, they can be star type or they can be delta type. Generally for generator, the star type of winding, they are preferred because we need less number of turns to generate higher amount of voltage, because line voltage is generally higher in case of star. The second advantage with the star winding is that we have a neutral, and in generator generally there can be faults. So in that case, if we have a neutral, so it can very easily be grounded, and the machine windings can be kept safe from these kind of faults. The rotor, the second part, rotating part of the machine. So, in synchronous machine there are two types of rotor, one is your salient type or second is non-salient type. If we see this type of rotor, this is called as cylindrical rotor or non-salient type of rotor. In this case we place windings, distributed winding, as you can see here we create it just like a cylinder, and we create slots and we put up windings in these slots. So, here the axial length of this rotor is slightly large as compared to the other rotor that we have, a salient pole type motor, where we have projected poles. If you see these poles, this pole, it is mounted over this structure, and this type of rotor is generally preferred for low speed applications, because we can place large number of projected poles. If we have higher pole machine, so we generally go for the salient type of rotor construction, and if we have to use lesser number of poles, like we can be seeing that 2 and 4 poles can be maximum placed, because winding becomes very complex in case we want to create more poles in non salient pole type machines. So, for higher application this type of constructions it is preferred. And the rotors is again having 2-3 major parts. One is the rotor core, that again is made of steel laminations. The laminations are used to reduce eddy current losses. We know that when we use laminations, they are insulated from each other, and whatever eddy currents are produced, they do not get in touch with each other, and as a result of that the net amount of eddy current loss that takes place, it is reduced. Second is the winding, and the windings is the field winding, they are placed on the rotor structure, particularly in this case. So, the field windings, they are energized by a DC source from external means, and we have slip rings through which the DC supply is given to the this field winding. Then we have this shaft which again made of your hard steel, which is used to rotate, because we need to rotate it, we need to create that rotating field. So, here once the field is created by supplying DC supply, and this is rotated by moving this shaft. So, this view is of the cylindrical rotor machines. We can see that the distribution of the flux. This is we can say the shape of the rotor, it appears like a cylinder. Here the winding, they are distributed, we call it distributed because it is distributed over its periphery, and the flux direction can be given depending upon the direction of this winding, and we can see the flux distribution over this. This is the salient pole type machine. In salient pole type machine, we have projected poles. As we can see, there are 4 poles. They are and the flux distribution is non-uniform in this case, because we see that the flux which is closer to these poles, the flux will be more in these cases, whereas if you see in this case the flux distribution will be uniform, because windings are placed almost over all the parts of the rotor. And the field is applied through the DC power source. There are 2 ways, either you supply the DC power from a source through the slip rings or the brushes. As we can see in this figure, we are this is what is used for supplying the DC power to the field winding. And say the second is, that is generally preferred nowadays, is that DC power from a special DC source mounted directly on the shaft of the machine. That is what we call as brushless exciter. So, in this case there is no physical contact, and as a result of that the maintenance part of this, it goes down. So, if you see the slip rings, they are metal rings which are encircling the shaft, as we can see that they are encircling this shaft, and one end of this rotor winding is connected to the So, the windings which are placed on the rotor, they are connected to the slip rings, and they basically take and give current to the windings through this. And stationary brush mounted on the machine's casing right on the each slip rings. The brushes, they are made of the carbon, and they have small conductivity because they are semiconductors, and they have very small friction, because we do not want to have higher friction that may result into certain losses and poor speed of the machines as well. So, DC supply is applied through the field winding during rotation. But the concept of excitation is changing now. Now we are having the brushless exciter. We are, with the development of semiconductor technology, we are using now power electronics devices for exciting purpose. So, brushless exciter is a small generator whose field winding is mounted on the stator and armature circuit is placed on the rotor shaft. So, what it is done? So, that armature which is placed on the rotor, it moves along with that machine, and the field, it is mounted on the stator, that that is used to generate EMF on that. Whatever EMF is generated on the rotor shaft, that is directly connected to the field winding of the armature, which ultimately generates the 3-phase supply in the stator windings. The exciters generators 3-phase output is rectified, because we need to have supply DC supply to the rotor field. So, we need to rectify that, because we are taking that supply, the AC supply, it is being rectified and then it is being supplied to the field winding. And it is possible to adjust the current on the main machine by controlling the small DC current, because I told you that we are having power electronic devices nowadays. So, we can adjust the firing angle of the switching devices like thyristor, which are used for rectifying this purpose, and the field current can be easily controlled, and there is no mechanical contact, and as a result of that, the exciter of this type, it requires very less maintenance, because there is no wear and tear of any material like your brushes in the earlier case. If you see the circuit diagram of this brushless exciter, we can see that you can see this is the rotor part and this is the stator part. In this case, what we have is that we take the 3-phase input low current. I told you this low current that can be taken, and it is being rectified, and it is applied to the exciter field of your exciter, which is placed on the stator, that is stationary part. On the rotor, I told you that the rotor winding, this exciter's armature, it is placed on the rotor. So, it is rotating along with that machine. So, whatever field is created, that armature which is revolving, it comes in contact with that, it will induce some EMF here, and that EMF is rectified, and then further it is applied to the synchronous machine. So, whenever we need to generate an EMF, we need to change the flux. So, here what we are doing, we are creating this flux through this field winding, and then since it is rotating, so that we can get a rotating magnetic field. So, field flux is changing here, and that flux, it gets linked with this armature which is stationary, which is placed on the stator, that we already discussed. So, that changing flux gets linked with these 3-phase windings, and as a result of that, we get an induced EMF according to Faraday's law of magnetic electromagnetic induction, that whenever the flux change takes place along a coil, an EMF is induced. Now, if you see in this case, we are taking that input from some external source, or it can also be taken from the synchronous generator itself, but here we can also place these permanent magnets. So, this is what we say is the pilot exciter. So, in this case we have a permanent magnet, it is going to create a field, and the field is ultimately, now it is exciting this, and it will induce an EMF here, because it is placed on the rotor, the magnets are placed on the rotor. So, that is again producing a changing field. As a result of that, we can have the EMF here, that is again rectified, and then exciter field. So, whatever the exciter that we have, its field is created now through this permanent magnet, whereas in this case we were taking this supply from the generator itself, but in this case we can have a permanent magnet, and further this field is again linked with the rotating armature, that again is rectified, because we need to supply DC to the field of your synchronous machine, and once we have this field, that rotating field, it gets linked with again the armature, stationary armature conductors, and as a result of that, an EMF is induced, which is taken as the output. The operating principle. Now, I told you that EMF is generated through static EMF method or dynamic EMF method. Either you keep your conductor stationary and rotate a magnetic field, or you rotate your conductor or keep your field stationary. So, in this case what we do, the rotor of a generator is driven by a prime mover. So, we place field winding over this and we rotate this prime mover. As a result of that, we get a rotating field, and the armature conductors, they are kept stationary. The rotating magnetic field is induced in a 3-phase voltage in the stator winding of the generator. So, that rotating field which is created by the rotor, that is getting linked with the conductors on your stator, and as a result of that, we are getting the 3-phase EMF. A simple principal operation can be understood by this example. If we see here, we have this permanent magnets, and these or electromagnetic rather, we can apply this DC supply, so that the magnets they are created, north and south pole can be created, and then we can rotate, and through this slip rings and brushes we can take an AC output. But revolving armature alternators, it is generally preferred in small alternators. I told you that in synchronous machine we place this armature conductor on stator, because the size of these windings is very huge, and as a result of that, if we place them on the rotor, so that can result into certain vibrations. So as a result of that, we can we need to keep those armature winding stationary, and we can rotate the field winding which is light in nature. So this is what we have. So what we can do here is that if you see that we can create this field and we can rotate this field, DC is applied through this battery here, through slip rings to the conductor. So it is this is rotating, it means it is creating a rotating field, and we are having these conductors, armature conductors, and EMF is induced in this, because we are simply changing that EMF, the flux, and flux change is linked with the coil, and ultimately we are getting an EMF depending upon the number of turns. This is what is the EMF generated in a synchronous machine. We can simply can drive this equation. It is simply given by the Faraday's law of electromagnetic conduction, that is E and d phi by dt when the flux change takes place. So if we calculate this EMF on this, let me show you that E, we know that we generally it is given by this and d phi by dt. So here in this case we have this number of turns, phi is the flux. So the flux is rotating in nature. So depending upon this, we can find out. So E, the fly, if it is rotating in nature, we can have this phi m sin omega t. So n d by dt, it can be given by phi sin omega t. As a result of that, if we simply solve it, we get it like this. So omega and phi is V maximum A and cos omega t, and this negative sign, it is given by the Lenz's law. Here this omega, it is 2 pi f and V maximum A cos omega t. If we take the RMS value, so that RMS value it gives you this under root 2 pi and C, and C is basically is the winding factors here, because in machines we need to see whether we have distributed winding, that also makes a difference. As a result of that, full pitched or short pitched winding. So depending upon that, the magnitude of the EMF in a particular phase, it is decided. Induced EMF, it depends upon the flux, the frequency, I told you, the speed of the rotation, and obviously the construction. Why construction? I told you that the winding factor, whether distributed winding, concentrated winding, so they are the factors which are also going to decide the amount of EMF. So this K, we can see here, it depends if this speed is equal to electrical speed, so it becomes equal to NC by root 2, and here if omega is equal to omega m. So this example can be I will in subsequent slides it will be clear that it depends upon the number of poles. If number of poles are 2 or what is the mechanical speed, so accordingly the EMF is the cycles are decided. If number of poles are 4, so in one rotation there can be 2 cycles. So that part we will get to know, but EMF in a particular phase can be given by this relation as it is shown here. So we have three phase winding which are placed over this, and in this case we can get these 3 phase EMF, and since there the placement of the windings is 120 degree apart, so we can get these 3 phase. You can keeping this VA as a reference. So VB will be 120 degree anti-clockwise to this, and then the VC, the phase voltage in the phase C. In 2 pole alternator, I told you that for one electrical cycle we can get a particular cycle, but if you have 4 poles and one rotation, we can get 2 such cycles. So the frequency, it is given by P n by 120. N is the number of rotor, P number of poles, and is 120. If the speed of the rotor it changes, that is why we need to have this fixed speed. If speed changes, frequency will change, and frequency will change, whole operation of the system can alter. So, that is why it is very important to keep the speed of the rotor constant. Here is that example that I wanted to tell you, is that if we have more number of poles, we can see here, if we have number of poles and these are the windings. So, in one rotation you can see how many cycle do we get. So, it is a 8 pole, and in case we have only 2 poles, so in one rotation how many cycle we will get one cycle only. So, this the frequency, it depends upon n p by 120 number. Obviously, how many poles are there, what is the rotational speed. So, that will ultimately decide the frequency of your supply that you are generating in your armature. Next comes the concept of this rotating magnetic field. In 3 phase machine, generally we have rotating magnetic field. We can see in this structure that this is the rotor view. We have 3 phase windings. A, let us suppose this is coil A, one end of this, and this is the A dash. This is 120 degree to this, B and B dash. This is C and C dash. So, this way these windings are placed, and we know that if you see this 3 phase supply structure earlier, in any of the winding, the current in phase A, if it is positive, if you see this here at that particular instant, this is B and C, the current is this is negative. It means that current is either entering through a particular phase or it is leaving through that particular phase. So, that is what is shown here. If you see the direction of the current, it is represented by an arrow. So, if you see the cross, so cross, it is going, if this cross means that current is leaving. If you see the dot, if you see from the front, so we can see a dot. So, current is coming towards you, and cross means current is leaving. So, that is what is the notation that is given in this case. In rotor structure, what we have, we can take a particular instant where we have the structure like this, a particular instant, that this we are A dash, then we have B and B dash, C and C dash. So, they are 120 degree apart from each other, and this notation can be easily obtained from the diagram that I shown you. And what we have here is that current is entering from coil A, it is leaving from coil A dash. So, it means if we have coil like this, A and A dash, and if we see this one, this is B, B dash, C, C dash. So, current can enter from this and it is leaving from these two. So, current goes out of these two, it enters from here, it leaves from these two. It means that is why that magnitude is shown. So, that is what is the notation that I have shown here, that these are the dots here and the cross on these positions. So, if we apply right hand thumb rule, right. So, in right hand thumb rule, current enters like this. So, what we have, the magnetic field direction can be given like this, because if we use this, we can the current shown by my finger, the thumb will be showing you the direction of the flux. So, that flux direction can be shown like this. So, here you can see that the change of the flux, that is changing after every instant, because we know the supply that we are applying, it is varying with time. So, we have 3 phase windings. So, in 3 phase winding, so they all are, so they all are you can see this. So, in this case, either first phase A, then phase B and then phase C, they are attaining their peak after every 60 degree. You can see this. The same change can be observed in these cases also, that the direction of the current is changing. So, it means that if current is entering from A at particular instant and leaving from A dash, next instant it will be entering from A dash and leaving from the A. So, this way the direction of the current is changing every instant, and as a result of that, this direction of the net magnetic field, it is changing. That is why we get this rotating magnetic field. Further, the armature reaction in synchronous machine is also very important. In this case, we see armature reaction, as its name suggests, it is simply the effect of the armature EMF that is generated. Whenever a rotor of the synchronous generator is rotating, a voltage is created, it is induced in the stator, that is quite obvious. When a load is connected, a current starts flowing through the stator, and once the current starts flowing to the stator, it also creates a magnetic field, because when current flows to the stator, a magnetic field is produced, and that magnetic field will also affect, it will come in contact with your rotor field, and as a result of that it can distort it. So, that is what is the effect of the armature EMF on the main field. So, we can see here in this case, this is the rotor MMF that is shown by the phasor. If we assume that the current that is being supplied through this machine to the stator, it is lagging behind by an angle, by some angle. So, it will induce an EMF or flux 90 degree to this. So, we can see this direction of the flux, that is 90 degree to the current. So, this is for the lagging load. So, we have two fields now, one is because of rotor, this is the stator. The net resultant field will be some phasor sum of these two, because these are phasor quantities. So, the net resultant is this Br plus Bs, as can be seen, this is net resultant current. So, similarly the voltage, we can see this total net flux density, it will be Br of rotor and the stator. The voltage will also be affected, because the armature reaction will also change the flux. Once the flux changes, ultimately the voltage at the terminals or that will also be changed. So, voltage phase voltage will be the voltage generated in the winding, plus it is the effect of that armature. This is how it affects the net amount of voltage, and we can represent it through this circuit diagram also. This voltage or armature reaction voltage can be given by minus j xi, because it is certain sort of drop, because armature is creating hindrance to the main EMF, the flux that is there. So, that is why this negative sign is given. So, net phase voltage will be equal to EA, whatever is the voltage being generated by the stator terminals, minus this particular drop, that is because of the armature reaction. So, armature reaction, it is modeled by this circuit. So, in addition to this, we also connect a load. So, net amount of voltage that appears across a terminal is, this is also taking into account the winding effect, because winding also have some self inductance, it also has some resistance. So, net amount of, there will be some drop in those resistance and the inductance of the winding. So, net amount of the voltage that appears on the terminals, because terminal voltage will be the net amount of voltage generated minus the drop in the windings, that is the resistive as well as the inductive drop, plus the drop because of the armature reaction. So, this is what is the final equation, voltage equation for the voltage that is appearing across the terminal. The armature reaction, it reacts differently for different power factor, because I told you that the early example that we have seen, it is for the lagging power factor, the current is lagging behind. So, it can be for leading or it can also be for the unity power factor. So, this is how it behaves. If you see this the phasor diagram, because they can be represented by the phasor quantities, alternating quantities. So, the phasor diagram for the unity power factor, the current is that is in phase with voltage. So, drop will also be in phase with that, and this is the drop because of this stator synchronous reactance, and this will be the net amount of voltage that we are getting. For lagging power factor, the current, this is the voltage phasor, this is the current, it is lagging behind by some angle, and the drop in the this resistance will be in phase with this R, because this is I and R, and the drop in the reactance will be 90 degree to this. So, we can have this, see if the IA and IARA, they are in parallel to each other, and this particular phasor IAXS will be 90 degree to this particular angle IA. For leading power factor, we see that this is the voltage phasor here and current is leading. So, the quantities are generally taken in anti-clockwise. So, if we observe from here, first current will appear, then the voltage phasor will come, and the drop in the resistance and in reactance is again shown similar. We see that this is the voltage, this is the drop IaRa drop, that is in again in phase with the current, and the drop in reactance it will be 90 degree to this current. So, that is we can see here. So, this is the net amount of voltage for the leading power factor. So, it is very interesting to see that for a given current and magnitude of load current, the terminal voltage is lowest for the lagging power factor and higher for the leading loads. So, we can see that